Welcome to Statistics and Data Science. I'm Barton Polson, and what we're going to be doing in this course is talking about some of the ways that you can use statistics to see the unseen, to infer what's there even when most of it's hidden. Now, this shouldn't be a surprise if you remember the data science Venn diagram that we talked about a while ago. We have math up here in the top right corner, but if you were to go to the original description of this Venn diagram, its full name was Math and Stats. And let me just mention something in case it's not completely obvious about why statistics matters to data science. And the idea is this: counting is easy. It's easy to say how many times a word appears in a document. It's easy to say how many people voted for a particular candidate in one part of the country. Counting is easy, but summarizing and generalizing, those things are hard. And part of the problem is there's no such thing as a definitive analysis. All analyses really depend on the purposes that you're dealing with. So as an example, let me give you a couple of pairs of words and try to summarize the difference between them in just 2 or 3 words. I mean, in a word or two, how is a souffle different from a quiche? Or how is an aspen different from a pine tree? Or how is baseball different from cricket? And how are musicals different from opera? It really depends on who you're talking to. It depends on your goals, and it depends on sort of the shared knowledge. And so there's not a single definitive answer. And then there's the matter of generalization. Think about, again, take music. Listen to 3 Concerti by Antonio Vivaldi, and do you think you can safely and accurately describe all of his music? Now, I actually chose Vivaldi on purpose because Igor Stravinsky said you could. He said he didn't write 500 concertos. He wrote the same concerto 500 times. But take something more real world like politics. If you talk to 400 registered voters in the US, can you then accurately predict the behavior of all of the voters? There's about 100 million voters in the US. And that's a matter of generalization. And that's the sort of thing that we try to take care of with inferential statistics. Now, there are different methods that you can use in statistics, and all of them are designed to give you sort of a map, a description of the data you're working with. There are descriptive statistics, there are inferential statistics, there's the inferential procedure, hypothesis testing, and there's also estimation. And I'll talk about each of those in more depth. There are a lot of choices that have to be made, and some of the things I'm going to discuss in detail are, for instance, the choice of estimators, that's different from estimation, different measures of fit, feature selection for knowing which variables are the most important in predicting your outcome, also common problems that arise when trying to model data, and the principles of model validation. But through this all, the most important thing to remember is that analysis is functional. It's designed to serve a particular purpose. And there's a very wonderful quote within the statistics world that says, all models are wrong. All statistical descriptions of reality are wrong because they're not exact depictions, they're summaries. But some are useful. And that's from George Box. And so really the question is, you're not trying to be totally, completely accurate, because in that case, you just wouldn't do an analysis. The real question is, are you better off doing your analysis than not doing it? And truthfully, I bet you are. So in sum, we can say 3 things. Number 1, you want to use statistics to both summarize your data and to generalize from one group to another if you can. On the other hand, there's no one true answer with data. You got to be flexible in terms of what your goals are and the shared knowledge. And no matter what you're doing, the utility of your analysis should guide you in your decisions. The first thing we want to cover in statistics and data science is the principle of exploring data. And this video is just designed to give an exploration overview. So we like to think of this, the intrepid explorers. They're out there exploring and seeing what's in the world. You can see what's in your data. More specifically, you want to see what your data set is like. You want to see if your assumptions are met so you can do a valid analysis with your chosen procedure. And really, something that may seem very weird is you want to listen to your data. If something's not working out, if it's not going the way you want, then you need to pay a little more attention, and exploratory data analysis is going to help you do that. Now, there are 2 general approaches to this. First off, there's a graphical exploration. So you use graphs and pictures and visualizations to explore your data. The reason you want to do this is that graphics are very dense in information. They're also really good, in fact, the best way to get the overall impression of your data. Second to that, there is numerical exploration. I make it very clear, this is the second step. Do the visualization first, then do the numerical part. Now, you want to do this because it can give greater precision, and this is also an opportunity to try variations on the data. You can actually do some transformations, move things around a little bit, and try different methods and see how that affects the results and see how it looks. So let's go first to the graphical part. There are very quick and simple plots that you can do. Those include things like bar charts and histograms and scatter plots. Very easy to make and very quick way of getting an understanding of the variables in your data set. In terms of numerical analysis, again, after the graphical methods, you can do things like transform the data, that is, take like the logarithm of your numbers. You can do empirical estimates of population parameters, and you can use robust methods. And I'll talk about all of those in more length in later videos. But for right now, I can sum it up this way. The purpose of exploration is to help you get to know your data. And also, you want to explore your data thoroughly before you start modeling it, before you build statistical models. And all the way through, you want to make sure you listen carefully so that you can find hidden or unassumed details and leads in your data. As we move in our discussion of statistics and exploring data, the single most important thing we can do is exploratory graphics. In the words of the late great Yankees catcher Yogi Berra, you can see a lot by just looking. That applies to data as much as it applies to baseball. Now, there's a few reasons you want to start with graphics. Number one is to actually get a feel for the data. I mean, what's it distributed like? What's the shape? Are there strange things going on? Also, it allows you to check the assumptions and see how well your data match the requirements of the analytical procedures you hope to use. You can check for anomalies like outliers and unusual distributions and errors. And also you can get suggestions. If something unusual is happening in the data, that might be a clue that you need to pursue a different angle or do a deeper analysis. Now, we want to do graphics first for a couple of reasons. Number one is they're very information dense, and fundamentally humans are visual. It's our single highest bandwidth way of getting information. It's also the best way to check for shape and gaps and outliers. There are a few ways you can do this if you want to. The first is with programs that rely on code. So you can use the statistical programming language R, the general purpose programming language Python. You can actually do a huge amount in JavaScript, especially in D3.js, or you can use apps that are specifically designed for exploratory analysis. That includes Tableau, both the desktop and the public versions, Click, and even Excel is a good way to do this. And then finally, if you really want to know, you can do this by hand. John Tukey, who's the father of exploratory data analysis, wrote his seminal book, a wonderful book, where it's all hand graphs, and actually it's a wonderful way to do it. But let's start the process for doing these graphics. We start with one variable, that is univariate distributions. And so you're going to get something like this. The fundamental chart is the bar chart. This is when you're dealing with categories and you're simply counting how many cases there are in each category. The nice thing about bar charts is they're really easy to read. Put them in descending order and maybe have them vertical, maybe have them horizontal. Horizontal can be nice to make the labels a little easier to read. This is about psychological profiles of the United States. This is real data, and that we have the most states in the friendly and conventional, a smaller number in temperamental and uninhibited, and the least common of the United States is relaxed and creative. Next, you can do a box plot, or sometimes called a box and whiskers plot. This is when you have a quantitative variable, something that's measured, and you can say how far apart scores are. A box plot shows quartile values. It also shows outliers. So for instance, this is Google searches for modern dance, and that's Utah at 5 standard deviations above the national average. That's where I'm from, and I'm glad to see that there. Also, it's a nice way to show many variables side by side if they're on approximately similar scales. Next, if you have quantitative variables, you're going to want to do a histogram. Again, quantitative, so interval or ratio level or measured variables. And these let you see the shape of a distribution and potentially compare many. So here are 3 histograms for Google searches on data science and entrepreneur and modern dance. And you can see mostly for the part normally distributed with a couple of outliers. Once you've done one variable or the univariate analyses, you're going to want to do two variables at a time. That is bivariate distributions or joint distributions. Now, one easy way to do this is with grouped plots. So you can do grouped bar charts and box plots. What I have right here is grouped box plots. I have my three regions, psychological regions of the United States, and I'm showing how they rank on openness. That's a psychological characteristic. And what you can see is that the relaxed and creative are highest and the friendly and conventional tend to go to the lowest. And that's kind of how that works. It's also a good way of seeing the association between a categorical variable like region of the United States psychologically and a quantitative outcome, which is what we have here with openness. Next, you can also do a scatter plot. That's where you have two quantitative variables. And what you're looking for here is it a straight line? That is it linear? Do we have outliers? And also the strength of association. How closely do the dots all come to the regression line that we have here in the middle? And this is an interesting one for me because we have openness across the bottom. So more open as you go to the right, and agreeableness. And what we see is there's a strong downhill association. The states in the United States that are the most open apparently are also the least agreeable. So we're going to have to do something about that. And then finally, you want to go to many variables. That is multivariate distributions. Now, one big question here is 3D or not 3D. Let me actually make an argument for not 3D. So what I have here is a 3D scatter plot of three variables about Google searches. Up the left, I have FIFA, which is for professional soccer. Down there on the bottom left, I have searches for NFL, and on the right, I have searches for NBA. Now, I did this in R, and what's neat about this is you can click and drag and move it around. And that's kind of fun. You kind of spin around, and it gets kind of nauseating as you look at it. And this particular version, I'm using Plotly in R. It allows you to actually click on a point and see, let me see if I can get the floor in the right place. You got to click on a point and see where it ranks on each of these characteristics. You can see, however, this thing's hard to control. And once it stops moving, it's not much fun. And truthfully, most 3D plots I've worked with are just kind of nightmares. They seem like they're a good idea, but not really. So here's the deal. 3D graphics, like the one I just showed you, because they're actually being shown in 2D, they have to be in motion for you to tell what's going on at all. And fundamentally, they're hard to read and confusing. Now, it's true they might be useful for finding clusters in 3 dimensions. We didn't see that in the data we had. But generally, I just avoid them like the plague. What you want to do, however, is see the connection between several variables. You might want to use a matrix of plots. This is where you have, for instance, many quantitative variables. You can use markers for group membership if you want. And I find it to be much clearer than 3D. So here I have the relationship between 4 search terms: NBA, NFL, MLB for Major League Baseball, and FIFA. You can see the individual distributions. You can see the scatter plots. You can get the correlation. Truthfully, this for me is a much easier kind of chart to read and get the richness that we need from a multidimensional display. So the questions you're trying to answer overall are, number one, do you have what you need? Do you have the variables you need? Do you have the variability that you need? Are there clumps or gaps in the distributions? Are there exceptional cases, anomalies that are really far out from everybody else, or spikes in the scores? And are there errors in data? Were there mistakes in coding? Did people forget to answer questions? Are there impossible combinations? And these kinds of things are easiest to see with a visualization that'll really just kind of puts it right there in front of you. And so in sum, I can say this about graphical exploration of data. It's a critical first step. This is basically where you always want to start. And you want to use the quick and easy methods. Again, bar charts, scatter plots are really easy to make, and they're very easy to understand. And once you're done with the graphical exploration, then you can go to the second step, which is exploring the data through numbers. The next step in statistics and exploring data is exploratory statistics, or numerical exploration of data. I like to think of this as go in order. First you do visualization, then you do the numerical part. And a couple of things to remember here. Number one is you're still exploring the data. You're not modeling yet, but you are doing a quantitative exploration. This might be an opportunity to get empirical estimates, that is, of population parameters as opposed to theoretically based ones. it's a good time to manipulate the data and explore the effects of manipulating the data, looking at subgroups, looking at transforming variables. Also, it's an opportunity to check the sensitivity of your results. Do you get the same general results if you test under different circumstances? So we're going to talk about things like robust statistics and resampling data and transforming data. So we'll start with robust statistics. This, by the way, is Hercules, a robust mythical character. And the idea with a robust statistics is that they are stable, is that even when the data varies in sort of unpredictable ways, you still get the same general impression. This is a class of statistics, it's an entire category, that's less affected by outliers and by skewness and kurtosis and other abnormalities in the data. So let's take a quick look. This is a very skewed distribution I created. The median, which is the dark line there in the box, is right around 1. And I'm going to look at two different kinds of robust statistics, the trimmed mean and the Windsorized mean. With the trimmed mean, you take a certain percentage of the data from the top and the bottom, you just throw it away and you compute the mean for the rest. With the Windsorized, you take those and then you move those scores into the highest non-outlying score. Now, the 0% is exactly the same as the regular mean, and here it's 1.24. But as we trim off 5% or move in 5%, you can see that the mean shifts a little bit. Then 10%, it comes in a little bit more to 25%. Now we're throwing away 50% of the data, 25% on the top, 25% on the bottom. And we get a mean here of 1.03, that's a trimmed mean, and a Windsorized of 1.07. When we throw away 50%, when we trim 50%, that actually means that we're leaving just the median. Only the middle score is left. Then we get 1.01. What's interesting is how close we get to that even when we have 50% of the data left. And so that's an interesting example of how you can use robust statistics to explore data even when you have things like strong skewness. Next is the principle of resampling. And that's like pulling marbles repeatedly out of a jar, counting the colors, putting them back in and trying again. That's an empirical estimate of sampling variability. So sometimes you get 20% red marble, sometimes you get 30, sometimes you get 22, and so on. There are several versions of this. They go by the names the jackknife and the bootstrap and the permutation. And the basic principle of resampling is also key to the process of cross-validation. I'll have more to say about validation later. And then finally, there's transforming variables. Here's our caterpillars in the process of transforming into butterflies. But the idea here is you take a sort of difficult data set and then you do what's called a smooth function. There's no jumps in it, and something that preserves the order, and it allows you to work on the full data set. So you can fix skewed data, and in a scatter plot, you might have a curved line. You can fix that. And probably the best way to look at this is with something called Tukey's ladder of powers. I mentioned before John Tukey, the father of exploratory data analysis. He talked a lot about transformations. This is his ladder starting at the bottom with the -1 over x squared up to the top with his x cubed. And here's how it works. This distribution over here is a symmetrical, normally distributed variable. And as you start to move in one direction, and you apply the transformation, you take the square root, you see how it moves the distribution over to one end. Then the logarithm, and you get to the end, you get this -1 over the square of the score. And that pushes it way, way, way over. If you go the other direction, for instance, you square the scores, it pushes it down in the one direction, you cube it, and then you see how it can move it around in ways that allow you to, you can actually undo the skewness to get back to a more centrally distributed distribution. And so these are some of the approaches that you can use in the numerical exploration of data. In sum, let's say this. Statistical or numerical exploration allows you to get multiple perspectives on your data. It also allows you to check the stability, see how it works with outliers and skewness and mixed distributions and so on. And perhaps most importantly, it sets the stage for the statistical modeling of your data. As a final step of statistics and exploring data, I'm going to talk about something that's not usually considered exploring, but is basic descriptive statistics. I like to think of it this way. You've got some data and you are trying to tell a story. More specifically, you're trying to tell your data's story. And with descriptive statistics, you can think of it as trying to use a little data to stand in for a lot of data, using a few numbers to stand in for a large collection of numbers. And this is consistent with the advice that we get from good old Henry David Thoreau, who told us, simplify, simplify. If you can tell your story with more carefully chosen and more informative data, go for it. So there's a few different procedures for doing this. Number one, you want to describe the center of your distribution of data. That's if you're going to pick a single number, use that. Two, if you can give a second number, give something about the spread or the dispersion or the variability. And three, it's also nice to be able to describe the shape of the distribution. Let me say more about each of these in turn. First, let's talk about center. We have the center of our rings here. Now, there are a few very common measures of center or location or central tendency of a distribution. There's the mode, and there's the median, and there's the mean. Now, there are many, many others, but those are the ones that are going to get you most of the way. Let's talk about the mode first. Now, I'm going to create a little data set here on a scale from 1 to 11, and I'm going to put individual scores. There is a 1 and another 1 and another 1 and another 1. Then we have a 2, 2. Then we have a score way over at 9 and another score over at 11. So we have 8 scores, and this is the distribution. This is actually a histogram of the data set. The mode is the most commonly occurring score or the most frequent score. Well, if you look at how tall each of these go, we've got more 1s than anything else. And so 1 is the mode because it occurs 4 times and nothing else comes close to that. The median is a little different. The median is looking for the score that is at the center if you split it into 2 equal groups. We have 8 scores, so we want to get one group of 4, that's down here, and then the other group of 4 is this really big one because it ranges way out. And the median is going to be the place on the number line that splits those into 2 groups. That's going to be right here at 1.5. Now the mean's a little more complicated, even though people understand means in general. It's the first one we have here that actually has a formula where m for the mean is equal to the sum of x, that's our scores on the variable, divided by n, the number of scores. You can also write it out with Greek notation if you want, like this, where that's sigma, a capital sigma is the summation sign, sum of x divided by n. And with our little data set, that works out to this. 1 plus 1 plus 1 plus 1 plus 2 plus 2 plus 9 plus 11. Add those all up and divide by 8 because that's how many scores there are. Well, that reduces to 28 divided by 8, which is equal to 3.5. If you go back to our little chart here, the 3.5 is right over here. You'll notice there aren't any scores really exactly right there. That's because the mean tends to get very distorted by outliers. It follows the extreme scores. But a really nice, I say it's more than just a visual analogy, is that if this number line were a seesaw, then the mean is exactly where the balance point or the fulcrum would be for these to be equal. People understand that. If somebody weighs more, they got to sit in closer to balance somebody who weighs less, who has to sit further out. And that's how the mean works. Now, let me give a little bit of the pros and cons of each of these. For the mode's really easy to do. You just count how common it is. On the other hand, it may not be close to what appears to be the center of the data. The median, it splits the data into 2 same-size groups, the same number of scores in each. And that's pretty easy to deal with, but unfortunately, it's hard to use that information in many statistics after that. And then finally, the mean. Of these 3, it's the least intuitive, it's the most effective by outliers and skewness, and that may really strike against it, but it is, however, the most useful statistically, and so it's the one that gets used the most often. Next, there's the issue of spread. Spread your tail feathers. And we have a few measures here that are very common also. There's the range, there are percentiles and interquartile range, and there's the variance and the standard deviation. I'll talk about each of those. First, the range. The range is simply the maximum score minus the minimum score. And in our case, that's just 11 minus 1, which is equal to 10. So we have a range of 10. And I can show you that here on our chart. It's just that line there at the bottom from the 11 down to the 1. That's a range of 10. The interquartile range, which actually is usually referred to simply as the IQR, is the distance between Q3, which is the 3rd quartile score, and Q1, which is the 1st quartile score. If you're not familiar with quartiles, it's the same as the 75th percentile score and the 25th percentile score. Really what it is you're going to throw away some of the data. So let's go to our distribution here. First thing we're going to do is we're going to throw away the two highest scores. There they are. They're grayed out now. And then we're going to throw away two of the lowest scores. They're out there. And then we're going to get the range for the remaining ones. Now, this is complicated by the fact that I've got this big gap in between 2 and 9. And different methods of calculating quartiles do something with that gap. So if you use a spreadsheet, it's actually going to do an interpolation process, and it'll give you a value of 3.75, I believe, and then down to 1 for the first quartile. So not so intuitive with this graph, but that is how it works usually. If you want to write it out, you can do it like this. The interquartile range is equal to Q3 minus Q1. And in our particular case, that's 3.75 minus 1. And that, of course, is equal to just 2.75. And there you have it. Now, our final measure of spread or variability or dispersion is two related measures, the variance and the standard deviation. These are a little harder to explain and a little harder to show. But the variance, which is at least the easiest formula, is this. The variance is equal to, that's the sum, the capital sigma is the sum of x minus m. That's how far each individual score is from the mean. And then you take that deviation there and you square it, you add up all the deviations, and then you divide by the number. So the variance is the average squared deviation from the mean. I'll try to show you that graphically. So here's our data set, and there's our mean right there at 3.5. Let's go to one of these 2's. We got a deviation there of 1.5. And if we make a square that's 1.5 points on each side, well, there it is. We can do a similar square for the other score at 2. If we're going down to 1, then it's going to be 2.5 squared, and it's going to be that much bigger. And we can draw one of these squares for each of our 8 points. The squares for the scores at 9 and 11 are going to be huge and go off the page, so I'm not going to show them. But once you have all those squares, you add up the area and you get the variance. So this is the formula for the variance, but now let me show the standard deviation, which is also a very common measure, is closely related to this. Specifically, it's just the square root of the variance. Now, there's a catch here. The formulas for the variance and the standard deviation are slightly different for populations and samples in that they use different denominators. But they give similar answers, not identical, but similar if the sample is reasonably large, say over 30 or 50, then it's going to be really just a negligible difference. So let's do a little pro and con of these three things. First, the range. It's very easy to do. It only uses two numbers, the high and the low, but it's determined entirely by those two numbers. And if they're outliers, you've got really a bad situation. The interquartile range, or IQR, it's really good for skewed data, and that's because it ignores extremes on either end. So that's nice. And the variance and the standard deviation, while they are the least intuitive and they are the most affected by outliers, they are also generally the most useful because they feed into so many other procedures that are used in data science. Finally, let's talk a little bit about the shape of a distribution. You can have symmetrical or skewed distributions, unimodal, uniform, or U-shaped. You can have outliers. There's a lot of variations. Let me show you a few of them. First off is a symmetrical distribution. Pretty easy. They're the same on the left and on the right. And this little pyramid shape is an example of a symmetrical distribution. There are also skewed distributions where most of the scores are on one end and then they taper off. This right here is a positively skewed distribution where most of the scores are at the low end and the outliers are on the high end. This is unimodal. It's our same pyramid shape. Unimodal means it has one mode, or really kind of one hump in the data. That's contrasted, for instance, to bimodal, where you have two modes. And that usually happens when you have two distributions that got mixed together. There's also uniform distributions where every response is equally common. There's U-shaped distributions where people tend to pile up at one end or the other and a big dip in the middle. And so there's a lot of different variations, and you want to get those, the shape of the distribution, to help you understand and put the numerical summaries, like the mean and like the standard deviation, and put those into context. In sum, we can say this. When you use descriptive statistics, that allows you to be concise with your data, tell the story, and tell it succinctly. You want to focus on things like the center of the data, the spread of the data, the shape of the data. And above all, watch out for anomalies because they can exercise really undue influence on your interpretations. But this will help you better understand your data and prepare you for the steps that follow. As we discuss statistics and data science, one of the really big topics is going to be inference. And I'll begin that with just a general discussion of inferential statistics. But I'd like to begin, unusually, with a joke. You may have seen this before. It says, there are two kinds of people in the world. One, those who can extrapolate from incomplete data. And the end, of course, because the other group is the people who can't. But let's talk about extrapolating from incomplete data or inferring from incomplete data. First thing you need to know is the difference between populations and samples. A population represents all of the data or every possible case in your group of interest. It might be everybody who's a commercial pilot. It might be whatever, but it represents everybody in that or every case in that group that you're interested in. And the thing about the population is it just is what it is. It has its values, it has its mean and standard deviation, and you are trying to figure out what those are because you generally use those in doing your analyses. On the other hand, samples, instead of being all of the data, are just some of the data. And the trick is they're sampled with error. You sample one group and you calculate the mean. It's not going to be the same if you do it the second time. And it's that variability that's in sampling that makes inference a little tricky. Now, also with inference, there are two very general approaches. There's testing, which is short for hypothesis testing. And maybe you've had some experience with this. This is where you assume that a null hypothesis of no effect is true. You get your data and you calculate the probability of getting the sample data that you have if the null hypothesis is true. And if that value is small, usually less than 5%, then you reject the null hypothesis, which says really nothing's happening, and you infer that there is a difference in the population. The other most common version is estimation, which is, for instance, characterizing confidence intervals. That's not the only version of estimation, but it's the most common. And this is where you use sample data to estimate a population parameter value directly. So you use the sample mean to try to infer what the population mean is. You have to choose a confidence level, you have to calculate your values, and you get high and low bounds for your estimate that work with a certain level of confidence. Now, what makes both of these tricky is the basic concept of sampling error. I have a colleague who demonstrates this with colored M&Ms. What percentage are red? And you get them out of the bags and you count. Now, let's talk about this. A population of numbers. I'm going to give you just a hypothetical population of the numbers 1 through 10. And what I'm going to do is I'm going to sample from those numbers randomly with replacement. That means I pull a number out, it might be a 1, and I put it back. I might get the 1 again. So I'm going to sample with replacement, which actually may sound a little bit weird, but it's really helpful for the mathematics behind inference. And here are the samples that I got. I actually did this with software. I got a 3, 1, 5, and 7. Okay, fine. Interestingly, that is almost all odd numbers, almost. My second sample is 4, 4, 3, 6, and 10. So you see I got the 4 twice, and I didn't get the 1, the 2, the 5, the 7, or 8, or 9. The third sample, I got 3 1s and a 10 and a 9. So we're way at the ends there. And then my fourth sample, I got a 3, 9, 2, 6, 5. All of these were drawn at random from the exact same population, but you see that the samples are very different. That's the sampling variability or the sampling error. And that's what makes inference a little trickier. And let's just say again, why the sampling variability, why it matters. It's because inferential methods like testing and like estimation try to see past the random sampling variation to get a clear picture on the underlying population. So in sum, let's say this about inferential statistics. You sample your data from the larger populations. And as you try to interpret it, you have to adjust for error. And there's a few different ways of doing that. And the most common approaches are testing or hypothesis testing and estimation of parameter values. The next step in our discussion of statistics and inference is hypothesis testing, a very common procedure in some fields of research. I like to think of it as put your money where your mouth is and test your theory. Here's the Wright brothers out testing their plane. Now, the basic idea behind hypothesis testing is this. You start with a question, and it's something like, what is the probability of X occurring by chance if randomness or meaningless sampling variation is the only explanation? Well, the response is this. If the probability of that data arising by chance when nothing's happening is low, then you reject randomness as a likely explanation. Okay, there's a few things I can say about this. Number one, it's really common in scientific research. Say, for instance, in the social sciences, it's used all the time. Number two, this kind of approach can be really helpful in medical diagnostics where you're trying to make a yes-no decision. Does a person have a particular disease? And three, really, anytime you're trying to make a go, no-go decision, which might be made, for instance, with a purchasing decision for a school district or implementing a particular law, you base it on the data and you have to make a yes-no. Hypothesis testing might be helpful in those situations. Now, you have to have hypotheses to do hypothesis testing. You start with H sub 0, which is the shorthand version for the null hypothesis. And what that is in and what that is in lengthier terms is that there is no systematic effect between groups. There's no association between variables, and random sampling error is the only explanation for any observed differences that you see. And then contrast that with H sub A, which is the alternative hypothesis. And this really just says that there's a systematic effect, that there is in fact a correlation between variables, that there is in fact a difference between two groups, that this variable does in fact predict the other one. Let's take a look at the simplest version of this, statistically speaking. Now, what I have here is a null distribution. This is a bell curve. It's actually the standard normal distribution, which shows z-scores and relative frequency. And what you do with this is you mark off what are called regions of rejection. And so I've actually shaded off the highest 2.5% of the distribution and the lowest 2.5%. What's funny about this is even though I draw it to plus and minus 3 and it looks like it hits 0, it's actually infinite and asymptotic. But that's the highest and lowest 2.5%. Collectively, that leaves 95% in the middle. Now, the idea is then you gather your data, you calculate a score for your data, and you see where it falls in this distribution. And I like to think of that as you have to go down one path or the other. You have to make a decision. And you have to decide whether to retain your null hypothesis, maybe it is random, or reject it and decide, no, I don't think it's random. The trick is things can go wrong. You can get a false positive. And this is when the sample shows some kind of statistical effect, but it's really randomness. And so, for instance, this scatter plot I have right here, you can see a little downhill association here, but this is in fact drawn from data that has a true correlation of 0. And I just kind of randomly sampled from it until I got this. It took about 20 rounds, but it looks negative, but there's really nothing happening. The trick about false positives is that's conditional on rejecting the null. The only way you can get a false positive is if you actually conclude that there's a positive result. It goes by the highly descriptive name of a type 1 error, but you get to pick a value for it, and 0.05 or a 5% risk if you reject the null hypothesis. That's the most common value. Then there's a false negative. This is when the data looks random, but in fact it is systematic or there's a relationship. So for instance, this scatter plot, it looks like it's pretty much a 0 relationship, but in fact this came from two variables that were correlated at 0.25. That's a pretty strong association. Again, I randomly sampled from the data until I got a set that happened to look pretty flat. And a false negative is conditional on not rejecting the null. You can only get a false negative if you get a negative. You say there's nothing there. It's also called a type 2 error. And this is a value that you have to calculate based on several elements of your testing framework. So it's something to be thoughtful of. Now, I do have to mention one thing, big security notice, but wait. The problem with hypothesis testing, there's a few. Number one, it's really easy to misinterpret it. A lot of people say, well, if you get a statistically significant result, it means that it's something big and meaningful. And that's not true because it's confounded with sample size and a lot of other things that just don't really matter. Also, a lot of people take exception with the assumption of a null effect or even a nil effect, that there's 0 difference at all. And that could be, in certain situations, it could be an absurd claim. So got to watch out for that. There's also bias from the use of a cutoff. Anytime you have a cutoff, you're going to have problems where you have cases that would have been just slightly higher, slightly lower. It would have switched on the dichotomous outcome. So that is a problem. And then a lot of people say that it just answers the wrong question because of what it's telling you is, What's the probability of getting this data at random? Well, that's not what most people care about. They want it the other way, which is why I mentioned previously Bayes' theorem, and I'll say more about that later. That being said, hypothesis testing is still very deeply ingrained, very useful in a lot of questions, and it's gotten us really far in a lot of domains. So in sum, let me say this. Hypothesis testing is very common for yes-no outcomes, and it's the default in many fields, and I'd argue that it is still useful and informative despite many of the well-substantiated critiques. We'll continue in statistics and inference by discussing estimation. Now, as opposed to hypothesis testing, estimation is designed to actually give you a number, give you a value, not just a yes, no, go, no go, but give you an estimate for a parameter that you're trying to get. I like to think of it as sort of a new angle, looking at something from a different way. The most common approach to this is confidence intervals. Now, the important thing to remember is this is still an inferential procedure. You're still using sample data and trying to make conclusions about a larger group or population. The difference here is instead of coming up with a yes, no, you instead focus on likely values for the population value. Most versions of estimation are closely related to hypothesis testing, sometimes seen as the flip side of the coin, and we'll see how that works in later videos. Now, I like to think of this as an ability to estimate any sample statistic, and there's a few different versions. We have parametric versions of estimation and bootstrap versions. That's why I got the boots here. And that's where you just kind of randomly sample from the data in an effort to get an idea of the variability. You can also have what are called central versus non-central confidence intervals in estimation, but we're not going to deal with those. Now, there are three general steps to this. First, you need to choose a confidence level, anywhere from, say, well, you can't have 0. It has to be more than 0, and it can't be 100%. Choose something in between. 95% is the most common. And what it does is it gives you a range of numbers, a high and a low. And the higher your level of confidence, the more confident you want to be, the wider the range is going to be between your high and your low estimates. Now, there's a fundamental trade-off in what's happening here, and it's the trade-off between accuracy, which means you're on target, or more specifically, that your interval contains the true population value. And the idea is that leads you to the correct inference. There's a trade-off between accuracy and what's called precision in this context. And precision means a narrow interval, and it's a small range of likely values. And what's important to emphasize is this is independent of accuracy. You can have one without the other, or neither or both. In fact, let me show you how this works. What I have here is a little hypothetical situation. I've got a variable that goes from maybe 10 to 90, and I've drawn a thick black line at 50. If you think of this in terms of percentages and political polls, it makes a very big difference if you're on the left or the right of 50%. And then I've drawn a dotted vertical line at 55 to say that that's our theoretical true population value. And then what I have here is a distribution that shows possible values based on our sample data. And what you get here is it's not accurate because it's centered on the wrong thing. It's actually centered on 45 as opposed to 55. And it's not precise because it's spread way out from maybe 10 up to almost 80. So this situation, the data is no help really at all. Now here's another one. This is accurate because it's centered on the true value. That's nice. But it's still really spread out. And you see that about 40% of the values are going to be on the other side of 50%. It might lead you to reach the wrong conclusion. So that's a problem. Now here's the nightmare situation. This is when you have a very, very precise estimate, but it's not accurate. It's wrong. And this leads you to a very false sense of security and understanding of what's going on. And you're going to totally blow it all the time. The ideal situation is this. You have an accurate estimate where the distribution of sample values is really close to the true population value and is precise. It's really tightly knit, and you can see that just about 95% of it is on the correct side of 50, and that's good. If you want to see all four of them here at once, we have the precise two on the bottom, the unprecise ones on the top, the accurate ones on the right, the inaccurate ones on the left. And so that's a way of comparing it. But no matter what you do, you have to interpret a confidence interval. Now, The statistically accurate way that has very little interpretation is this. You would say the 95% confidence interval for the mean is 5.8 to 7.2. Okay, so that's just kind of taking the output from your computer and sticking it into sentence form. The colloquial interpretation of this goes like this. There's a 95% chance that the population mean is between 5.8 and 7.2. Well, in most statistical procedures, specifically frequentist as opposed to Bayesian, you can't do that. That implies that the population mean shifts. That's not usually how people see it. Instead, a better interpretation is this. 95% of confidence intervals for randomly selected samples will contain the population mean. Now I can show you this really easily with a little demonstration. This is where I randomly generated data from a population with a mean of 55, and I got 20 different samples. And I got the confidence interval for each sample, and I've charted the high and the low. And the question is, did it include the true population value? And you can see that of these 20, 19 of them included it. Some of them barely made it. If you look at sample number 1 on the far left, barely made it. Sample number 8, it doesn't look like it made it. Sample 20 on the far right, barely made it on the other end. Only one of them missed it completely, that's sample number 2, which is shown in red on the left. Now, it's not always just 1 out of 20. I actually had to run the simulation about 8 times because it gave me either 0 or 3 or 1 or 2. And I had to run it until I got exactly what I was looking for here. But this is what you would expect on average. So let's say a few things about this. There are some things that affect the width of a confidence interval. The first is the confidence level, or CL. Higher confidence levels create wider intervals. The more certain you have to be, you're going to give a bigger range to cover your bases. Second, the standard deviation, where larger standard deviations create wider intervals. If the thing that you're studying is inherently really variable, then of course your estimate of the range is going to be more variable as well. And then finally there's the N, or the sample size. This one goes the other way. Larger sample sizes create narrower intervals. The more observations you have, the more precise and the more reliable things tend to be. I can show you each of these things graphically. Here we have a bunch of confidence intervals where I'm simply changing the confidence level from 0.50 at the left side up through 0.999. And you can see it gets much bigger as we increase. Next one is standard deviations. As the sample standard deviation increases from 1 to 16, you can see that the interval gets a lot bigger. And then we have sample size going from just 2 up to 512. I'm doubling it at each point. And you can see how the interval gets more and more and more precise as we go through. And so let's say this to sum up our discussion of estimation. Confidence intervals, which are the most common version of estimation, focus on the population parameter. And the variation in the data is explicitly included in that estimation. Also, you can argue that they're more informative because not only do they tell you whether the population value is likely, but they give you a sense of the variability of the data itself. And that's one reason that people argue that confidence intervals should nearly always be included in any statistical analysis. As we continue our discussion of statistics and data science, we need to talk about some of the choices that you have to make, some of the trade-offs, and some of the effects that these things have. We'll begin by talking about estimators, and that is different methods for estimating parameters. I like to think of this as what kind of measuring stick or standard are you going to be using? Now, we'll begin with the most common. This is actually called OLS, which is short for ordinary least squares. This is a very common approach. It's used in a lot of statistics, and it's based on what's called the sum of squared errors. And it's characterized by an acronym called BLUE, which stands for Best Linear Unbiased Estimator. Let me show you how that works. Let's take a scatter plot here of an association between two variables. This is actually the speed of a car and the distance to stop from about the 20s, I think. We have a scatter plot here, and we can draw a straight regression line through it. Now, the line that I've used is in fact the best linear unbiased estimate, but the way that you can tell that is by getting what are called the residuals. If you take each data point and draw a perfectly vertical line up or down to the regression line, because the regression line predicts what the value would be for that value on the x-axis, Those are the residuals. Each of those individual vertical lines is a residual. You square those and you add them up, and this regression line, the gray angled line here, will have the smallest sum of squared residuals of any possible straight line that you can run through it. Now, another approach is ML, which stands for maximum likelihood. And this is when you choose parameters that make the observed data most likely. It sounds kind of weird, but I can demonstrate it. And it's based on a kind of local search. It doesn't always find the best. I like to think of it like a person here with binoculars, looking around them, trying hard to find something, but you could theoretically miss something. Let me give a very simple example of how this works. Let's assume that we're trying to find parameters that maximize the likelihood of this dotted vertical line here at 55. And I've got three possibilities. I've got my red distribution, which is off to the left, the blue, which is a little more center, and the green, which is far to the right. And these are all identical, except they have different means. And by changing the means, you see that the one that is highest where the dotted line is the blue one. And so if only thing we're doing is changing the mean and we're looking at these three distributions, then the blue one is the one that has the maximum likelihood for this particular parameter. On the other hand, we could give them all the same mean right around 50 and vary their standard deviations instead. And so they spread out different amounts. In this case, the red distribution is highest at the dotted vertical line, and so it has the maximum value. Or if you want to, you can vary both the mean and the standard deviation simultaneously. And here the green gets a slight advantage. Now, this is really a caricature of the process because obviously you would just want to center it right there on the 55 and be done with it. The question is when you have many variables in your data set, then it's a very complex process of choosing values that can maximize the association between all of them. But you get a feel for how it works with this. The third approach that's pretty common is something called map for maximum a posteriori. This is a Bayesian approach to parameter estimation. And what it does is it adds the prior distribution and then it goes through sort of an anchoring and adjusting process. What happens, by the way, is that stronger prior estimates exert more influence on the estimate. And that might mean, for instance, a larger sample or more extreme values. And those have a greater influence on the posterior estimate of the parameters. Now, what's interesting is that these three methods all connect with each other. Let me show you exactly how they connect. The ordinary least squares, OLS, this is equivalent to maximum likelihood when it has normally distributed error terms. And maximum likelihood, ML, is equivalent to maximum a posteriori, or MAP, with a uniform prior distribution. You want to put it another way, ordinary least squares, or OLS, is a special case of maximum likelihood. And then maximum likelihood, or ML, is a special case of maximum a posteriori. And just in case you like it, we can put it in set notation. OLS is a subset of ML, is a subset of MAP. And so there are connections between these three methods of estimating population parameters. Let me just sum it up briefly this way. The standards that you use, OLS, ML, MAP, they affect your choices and the ways that you determine what parameters best estimate what's happening in your data. Several methods exist, and there's obviously more than what I showed you right here, but many are closely related, and under certain circumstances, they're all identical. And so it comes down to exactly what are your purposes and what do you think is going to best work with the data that you have to give you the insight that you need in your own project. The next step we want to consider in our statistics and data science and the choices that we have to make has to do with measures of fit, or the correspondence between the data that you have and the model that you create. Now, it turns out there's a lot of different ways to measure this, and one big question is how close is close enough? Or how can you see the difference between the model and reality? Well, there's a few really common approaches to this. The first one is what's called R squared. It's got a longer name. That's the coefficient of determination. There's a variation, adjusted R squared, which takes into consideration the number of variables. Then there's minus 2LL, which is based on the likelihood ratio, and a couple of variations, the Akaike Information Criterion, or AIC, and the Bayesian Information Criterion, or BIC. And then there's also chi-squared. Now that's actually a Greek C there. It looks like an X, but it's a C. And that's chi-squared. And so let's talk about each of these in turn. First off is R squared. This is the squared multiple correlation, or the coefficient of determination. And what it does is it compares the variance of Y. So if you have an outcome variable, it looks at the total variance of that and compares it to the residuals on Y after you've made your prediction. The scores on R squared range from 0 to 1, and higher is better. The next is -2 log likelihood. That's the likelihood ratio, or as I just said it, the -2 log likelihood. And what this does is it compares the fit of nested models. We have a subset, then a larger set, then a larger set overall. This approach is used a lot in logistic regression when you have a binary outcome. And in general, smaller values are considered better fit. Now, as I mentioned, there are some variations of this. I like to think of variations of chocolate. The -2 log likelihood, there's the Akaike information criterion, the AIC, and the Bayesian information criterion, BIC. And what both of these do is they adjust for the number of predictors. Because obviously, if you have a huge number of predictors, you're going to get a really good fit, but you're probably going to have what's called overfitting, where your model is tailored too specifically to the data you currently have and doesn't generalize well. These both attempt to reduce the effect of overfitting. And then there's chi-squared again. It's actually a lowercase Greek c, looks like an X. And chi-square is used for examining the deviations between two data sets, specifically between the observed data set and the expected values, or a model you create of we expect this many frequencies in each category. Now, I'll just mention, like going to the store, there's a lot of other choices, but these are some of the most common standards, particularly the R squared. And I just want to say, in sum, there are many different ways to assess the fit, the correspondence between a model and your data. And the choices affect the model, especially, are you going to penalize for throwing in too many variables relative to your number of cases? Are you dealing with a quantitative or a binary outcome? Those things all matter. And so the most important thing, as always, my standing advice is keep your goals in mind and choose a method that seems to fit best with your analytical strategy and the insight you're trying to get from your data. The statistics and data science offers a lot of different choices. One of the most important is going to be feature selection, or the choice of variables to include in your model. It's sort of like confronting this enormous range of information and trying to choose what matters most, trying to get the needle out of the haystack. The goal of feature selection is to select the best features or variables and get rid of uninformative and noisy variables and simplify the statistical model that you're creating, because that helps avoid overfitting or getting a model that works too well with the current data and works less well with other data. The major problem here is multicollinearity, a very long word that has to do with the relationship between the predictors and the model. I can show it to you graphically here. Imagine, for instance, we've got a big circle here to represent the variability in our outcome variable. We're trying to predict it. And we've got a few predictors. So we've got predictor number 1 over here, and you see it's got a lot of overlap. That's nice. Then we've got predictor number 2 here. It also has some overlap with the outcome, but it also overlaps with predictor 1. And then finally down here, we've got predictor 3, which overlaps with both of them. And the problem arises the overlap between the predictors and the outcome variable. Now, there's a few ways of dealing with this. Some of these are pretty common. So for instance, there's the practice of looking at probability values in regression equations. There are standardized coefficients, and there's variations on sequential regression. There are also newer procedures for dealing with the disentanglement of the association between the predictors. There's something called commonality analysis. There's dominance analysis, and there are relative importance weights. Of course, there are many other choices in both the common and the newer, but these are a few that are worth taking a special look at. First is p-values, or probability values. This is the simplest method because most statistical packages will calculate probability values for each predictor, and they'll put little asterisks next to it. And so what you're doing is you're looking at the p-values, the probabilities for each predictor, or more often the asterisks next to it, which sometimes give it the name of star search. You're just kind of cruising through a large output of data and just looking for the stars or asterisks. This is fundamentally a problematic approach for a lot of reasons. The problem here is you're looking individually and it inflates false positives. Say you have 20 variables, each is entered and tested with an alpha or false positive of 5%. You end up with nearly a 65% chance of at least one false positive in there. It's distorted by sample size because with a large enough sample, anything becomes statistically significant. And so relying on p-values can be a seriously problematic approach. Slightly better approach is to use betas or standardized regression coefficients. And this is where you put all the variables on the same scale. So usually standardized from 0 and then to either -1 + 1 or with a standard deviation of 1. The trick is though, they're still in the same context of each other and you can't really separate them because those coefficients are only valid when you take that group of predictors as a whole. So one way to try to get around that is to do what they call stepwise procedures, where you look at the variables in sequence. There are several versions of sequential regression that allow you to do that. You can put the variables into groups or blocks and enter them in blocks and look at how the equation changes overall. You can examine the change in fit at each step. The problem with a stepwise procedure like this is it dramatically increases the risk of overfitting, which again is a bad thing if you want to generalize your data. And so to deal with this, there's a whole collection of newer methods. A few of them include commonality analysis, which provides separate estimates for the unique and shared contributions of each variable. Well, that's a neat statistical trick, but the problem is it just moves the problem of disentanglement to the analyst. So you're really not better off than you were as far as I can tell. There's dominance analysis, which compares every possible subset of predictors. Again, sounds really good, but you have the problem known as the combinatorial explosion. If you have 50 variables that you could use, and there are some that have millions of variables, with 50 variables, you have over 1 quadrillion possible combinations. You're not going to finish that in your lifetime. And it's also really hard to get things like standard errors and perform inferential statistics with this kind of model. And then there's also something that's even more recent than these others called relative importance weights. And what this does is it creates a set of predictors that are orthogonal or uncorrelated with each other, basing them off of the originals. And then it predicts the scores, and then it can predict the outcome without the multicollinear because these new predictors are uncorrelated. It then rescales the coefficients back to the original variables. That's the back transform. And then from that, it assigns relative importance or a percentage of explanatory power to each predictor variable. Now, despite this very different approach, it tends to have results that resemble dominance analysis. It's actually really easy to do. Their websites, you just plug in your information and it does it for you. And so that's yet another way of dealing with the problem of multicollinearity and trying to disentangle the contribution of different variables. In sum, let's say this. What you're trying to do here is choose the most useful variables to include into your model. Make it simpler, be parsimonious. Also, reduce the noise and distractions in your data. And in doing so, you're going to always have to confront the ever-present problem of multicollinearity or the association between the predictors in your model with several different ways of dealing with that. The next step in our discussion of statistics and the choices you have to make concerns common problems in modeling. And I like to think of this as the situation where you're up against the rock and the hard place, and this is where the going gets very hard. Common problems include things like non-normality, non-linearity, multicollinearity, and missing data, and I'll talk about each of these. Let's begin with non-normality. Most statistical procedures like to deal with nice, symmetrical, unimodal bell curves. They make life really easy. But sometimes you get really skewed distributions or you get outliers. Skewness and outliers, well, they happen pretty often. They're a problem because they distort measures like the mean gets thrown off tremendously when there are outliers, and they throw off models because they assume the symmetry and the unimodal nature of a normal distribution. Now, one way of dealing with this that I've mentioned before is to try transforming the data, take the logarithm, try something else. But another problem may be that you have mixed distributions. If you have a bimodal distribution, maybe what you really have here is two distributions that got mixed together, and you may need to disentangle them through exploring your data a little bit more. Next is nonlinearity. The gray line here is the regression line. We like to put straight lines through things because it makes the description a lot easier. But sometimes the data is curved, and this is, you have a perfect curved relationship here, but a straight line doesn't work with that. Linearity is a very common assumption of many procedures, especially regression. To deal with this, you can try transforming one or both of the variables in the equation, and sometimes that manages to straighten out the relationship between the two of them. Also, using polynomials, things that specifically include curvature, like squares and cubed values, that can help as well. Then there's the issue of multicollinearity, which I've mentioned previously. This is when you have correlated predictors, or rather, the predictors themselves are associated with each other. The problem is this can distort the coefficients you get in your overall model. Some procedures, it turns out, are less affected by this than others. But one overall way of using this might also simply be to try use fewer variables. If they're really correlated, maybe you don't need all of them. And there are empirical ways to deal with this, but truthfully, it's perfectly legitimate to use your own domain expertise and your own insight to the problem, to use your theory to choose among the variables that would be the most informative. Part of the problem we have here is something called the combinatorial explosion. This is where combinations of variables or categories grow too fast for analysis. Now, I've mentioned something about this before. If you have 4 variables and each variable has 2 categories, then you got 16 combinations. Fine, you can try things 16 different ways. That's perfectly doable. If you have 20 variables with 5 categories, again, that's not too unlikely. You have 95 trillion combinations. That's a whole other ballgame, even with your fast computer. A couple of ways of dealing with this. Number one is with theory. Use your theory and your own understanding of the domain to choose the variables or categories with the greatest potential to inform. You know what you're dealing with. Rely on that information. Second is there are data-driven approaches. You can use something called a Markov chain Monte Carlo model to explore the range of possibilities without having to go through every single one of your 95 trillion combinations. Closely related to the combinatorial explosion is the curse of dimensionality. This is when you have phenomena. You got things that may only occur in higher dimensions or variable sets, things that don't show up until you have these unusual combinations. That may be true of a lot of how reality works, but the project of analysis is simplification. And so you got to try to do maybe one or two different things. You can try to reduce, mostly that means reducing the dimensionality of your data. Reduce the number of dimensions or variables before you analyze. You're actually trying to project the data onto a lower dimensional space, the same way you try to get a shadow of a 3D object. There's a lot of different ways to do that. There are also data-driven methods, and the same method here, a Markov chain Monte Carlo model, can be used to explore a wide range of possibilities. Finally, there's the problem of missing data, and this is a big problem. Missing data tends to distort analyses and it creates biases if it's a particular group that's missing. And so when you're dealing with this, what you have to do is actually check for patterns in missingness. You create a new variable that indicates whether a value is missing, and then you see if that's associated with any of your other variables. If there's not strong patterns, then you can impute missing values. You can put in the mean or the median. You can do regression imputation, something called multiple imputation, a lot of different choices. And those are all more technical topics that we'll have to talk about in a later, more technically oriented series. But for right now, in terms of the problems that can come up during modeling, I can summarize it this way. Number one, check your assumptions at every step. Make sure that the data have the distribution that you need. Check for the effects of outliers. Check for ambiguity and bias. See if you can interpret what you have, and use your analysis, use data-driven methods, but also your knowledge of the theory and the meaning of things in your domain to inform your analysis and find ways of dealing with these problems. As we continue our discussion of statistics and the choices that are made, one important consideration is model validation. And the idea here is as you're doing your analysis, are you on target? More specifically, your model that you create through regression or whatever you do, your model fits the sample data beautifully, you've optimized it there, but will it work well with other data? Fundamentally, this is the question of generalizability, also sometimes called scalability, because you're trying to apply it in other situations. And you don't want to get too specific or it won't work in other situations. Now, there are a few general ways of dealing with this and trying to get some sort of generalizability. Number one is Bayes, a Bayesian approach. Then there's replication. Then there's something called holdout validation, and then there's cross-validation. I'll discuss each of these very briefly in conceptual terms. The first one is Bayes, and the idea here is you want to get what are called posterior probabilities. Most analyses give you a probability value for the data given the hypothesis, so you have to start with an assumption about the hypothesis. But instead, it's possible to flip that around by combining it with special kinds of data to get the probability of the hypothesis given the data. And that is the purpose of Bayes' theorem, which I've talked about elsewhere. Another way of finding out how well things are going to work is through replication. That is, do the study again. It's considered the gold standard in many different fields. The question is whether you need an exact replication or a conceptual one that is similar in certain respects. You can argue for both ways, but one thing you want to do is when you do a replication, then you actually want to combine the results. And what's interesting is the first study can serve as the Bayesian prior probability for the second study. So you can actually use meta-analysis or Bayesian methods for combining the data from the two of them. Then there's holdout validation. This is where you build your statistical model on one part of the data and you test it on another. I like to think of it as the eggs in separate baskets. The trick is that you need a large sample in order to have enough to do these two steps separately. On the other hand, it's also used very often in data science competitions as a way of having a sort of gold standard for assessing the validity of a model. Finally, I'll just mention one more, and that's cross-validation. This is when you use the same data for both training and for testing or validating. There's several different versions of it, and the idea is you're not using all the data at once, but you're kind of cycling through and weaving the results together. There's leave one out, where you leave out one case at a time, also called LOO, L-O-O. There's leave P out, where you leave out a certain number at each point. There's K-fold, where you split the data into, say, for instance, 10 groups, and you leave out one and you develop it on the other 9, and then you cycle through. And there's repeated random subsampling, where you use a random process at each point. Any of those can be used to develop the model on one part of the data and test it on another, and then cycle through to see how well it holds up under different circumstances. And so, in sum, I can say this about validation. You want to make your analysis count by testing how well your model holds up from the data you developed it on to other situations, because that's really what you're trying to accomplish. This allows you to check the validity of your analysis and your reasoning, and it allows you to build confidence in the utility of your results. To finish up our discussion of statistics and data science and the choices that are involved, I want to mention something that really isn't a choice, but more an attitude. It's DIY for do it yourself. The idea here is, really, you just need to get started. Remember, data is democratic. It's there for everyone. Everybody has data. Everybody works with data, either explicitly or implicitly. So data is democratic. So is data science. And really, my overall message is you can do it. A lot of people think you have to be at this totally cutting edge virtual reality sort of thing. And it's true. There's a lot of active development going on in data science. There's always new stuff. The trick, however, is the software that you can use to implement those things often lags. It'll show up first in programs like R and Python, but as far as it showing up in a point-and-click program, that could be years. What's funny, though, is often these cutting-edge developments don't really make much of a difference in the results of the interpretation. They may in certain edge cases, but Usually not a huge difference. And so I'm just going to say, analysts beware. You don't necessarily have to do it. It's pretty easy to do them wrong. And so you don't have to wait for the cutting edge. Now, that being said, I do want you to pay attention to what you're doing. A couple of things I've said repeatedly is know your goal. Why are you doing this study? Why are you analyzing the data? What are you hoping to get out of it? Try to match your methods to your goal. Be goal directed. Focus on the usability. Will you get something out of this that people can actually do something with? And then, as I've mentioned several times with the Bayesian thing, don't get confused with probabilities. Remember that priors and posteriors are different things, just so you can interpret things accurately. Now, I want to mention something that's really important to me personally, and that is beware the trolls. You will encounter critics, people who are very vocal and who can be harsh and grumpy and really just intimidating. And they can really make you feel like you shouldn't do stuff because you're going to do it wrong. But the important thing to remember is the critics can be wrong. Yes, you'll make mistakes. Everybody does. I can't tell you how many times I have to write my code more than once to get it to do what I want it to do. But in analysis, nothing is completely wasted if you pay close attention. I've mentioned this before. Everything signifies, or in other words, everything has meaning. The trick is that the meaning might not be what you expected it to be. So you're going to have to listen carefully. And I just want to reemphasize, all data has value, so make sure you're listening carefully. In sum, let's say this, no analysis is perfect. The real question is not, is your analysis perfect, but can you add value? And I'm sure that you can. And fundamentally, data is democratic. So I'm going to finish with one more picture here. And that is, just jump right in and get started. You'll be glad you did.